Now in this video, we will be plotting the simple zero, simple pole, quadratic zero, and the quadratic pole. For the simple zero, this is something that you can see on the transfer function that looks like a 1 plus j omega over z1. So after converting the transfer function into a standard form, see something like that. So that is a simple zero. So the magnitude of this, well, so you convert this one into its polar form, so we'll get a magnitude that is like this. Uh, and the phase mode plot would be the inverse tangent omega over z1. Okay. Now, how do we plot this? Now, the exact mode plot for this magnitude of the simple zero would be like this. Okay. So it is 0 for smaller values of omega, and it rises as omega increases in factors of z sub 1. Now, to simplify our Bode plots, we don't normally use the exact plot, and instead we use what is called the straight line Bode plot. So the red line here shows the straight line Bode plot, and this plot has a zero value at omega equals z sub 1 instead of 3 dB. And after z sub 1, it makes a slope equals to positive 20 dB per decade. Okay. Now um, for the angle, the exact plot would look like this. And again, we approximate this into something like this. So it is also a straight line Bode plot for the angle. So at point 1 of z1, instead of 5.1, it has a value of 0 degrees for omega equals 0.1 z1. And after that, it makes a 45 degree per decade slope up to 10 z1, after which it is flat. Now um, before we go to simple pole, so we have some important uh, frequencies here. So the frequency where the red line changes slope, we call it the break or the corner frequency. So in this case, we have a break frequency of Z1. But take note that the exact value of the magnitude is actually 3 dB instead of 0. Now for the simple pole, so again we get the magnitude and the phase angles, and then plot it. So we have the blue line here as the exact plot, but we approximate it again with a straight line Bode plot that is 0 at omega equals p sub 1, but makes a slope of negative 20 dB per decade after that. Now for the angle, uh, we also approximate it by this line. So at 0.1 p1 omega, uh, before that, so the angle is 0 and make a slope of negative 45 degrees per decade up to 10 p sub 1 of omega, after which it becomes a flat line. So take note that in this simple pole, the break frequency is at omega equals p sub 1. Now for quadratic 0, this is a bit more complicated. So if you get the magnitude, it would be like this. And how do we plot this one? So first we make an assumption that omega is very much less than omega k. Uh, so in this case, HDB would be approximately equals to 0. For omega, which is much greater than omega k, HDB would be approximately 40 log of omega over omega k. At exactly omega equals omega k, we'll have negative 20 log of Q1. Now, Q1 here is what we call the quality factor. Now, to plot this, first we plot what is called the asymptote for low frequencies. So, for omega much less than omega k, we have this asymptote. For omega much greater than omega k, we have this asymptote. And we also plot the HDB at exactly omega equals omega k. And we make the plot. So as you can see, at omega equals omega k, the value of h of dB is not equals to 0, but it is negative 20 log Q1. No? This would be for values of Q1 that is between 0 and 1. Now for Q that is greater than 1, this will be the plot. Now take note that this line here makes a 20 dB per decade because of the presence of the 40 log omega over omega k. Now we could do the same for the angle, and that will look like this. And for quadratic pole, we also do the same strategy as we did for quadratic 0. So we first get the asymptotes at omega much less than omega n and much greater than omega n. So for Q that is um, um, much less than between 0 and for Q2 between 0 and 1, we'll get this plot, while for Q greater than 1, we'll get this plot. So again, at omega equals omega n, it is not a 0, and this line makes a 40 dB per decade. Okay, now the baseboard plot for quadratic pole would look like this, where omega A and omega B are defined as these formulas.